Okay, let's try this example again. Hopefully you can see this screen. It's the exact final example from mapping direct mapped cache. Now we're going to introduce set associative cache. So the question was, how many bits make up the tagline word? Memory is 1 cell per word, 16-bit address, 128 kilobytes total. Cache was direct mapped, had 8 lines and 32 words per line. The answer with all the arithmetic came out to be 8-bit tag, 3-bit line, 5-bit word, 16-bit address. So what I'm going to change now is, instead of a direct mapped cache, I'm going to make this a 4-way set associative cache. I made up the 4. I could have picked 2, 4, 8, 16. Well, I guess the most I could have picked here is 1, 2, 4, or 8. A 1-way set associative cache is a direct mapped cache. A 4-way set associative cache means 2 things. There are 4 lines per set, whatever that means. And here's what it means. Main memory blocks are mapped to sets, not to lines. So if I were going to draw this entire memory, the cache memory, 8 lines, looks like that. A direct map cache would have 8 lines. This 8-line 4-way set associative cache has 8 lines. In the previous example, you could have main memory block 0, let's say, 32 words per line, would have cells 0 to 31. It would get mapped to line 0. Now, with a 4-way set associative cache, there are 4 lines per set. So forget the line number. We have a set number, set 0, set 1. So main memory block 0, which has cells 0 to 31, is now mapped to 4 possible lines. Somewhere in set 0, main memory block 1, which has cells 32 to 63, since there are 2 to the 5, or 32 words in a line, there are 32 words in a block, 32 cells. We're going to stick with 1 cell per word through this course. So main memory block 1 would go somewhere in set 1. The answer is where? Now you need an algorithm. And we're going to use the least recently used algorithm in this whole course. LRU. Whenever you have a set associative cache, you need to be told how many lines are there per set, in this case 4, and what's the algorithm to decide which of those 4 lines in the set does the block go. So the answer is, it's going to replace or eject or evict the least recently used line that was in there. So main memory block 0, or 2, or 4, or 6, or 8, any of the main memory blocks with an even number could end up here, 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 or here. Never there, never there, never there, never there. Always somewhere in set 0. And if you ran this same computer program many times, the block could end up there sometimes, there sometimes, there, there. It depends on the programs that are running and which line or block was least recently used. That's the one that will get evicted. This will make good use of temporal locality. You should remember that. These are good online quiz questions. To make use of temporal locality, you want to keep the most recently used lines in the cache. So therefore, evicting the least recently used line is a good algorithm. If we're going to do this properly, we need to keep track of some kind of timestamp. If this was here, let's say Wednesday, Thursday, Friday, Saturday, and today is Sunday, well, this was just used yesterday, 2 days ago, 3 days ago, not since 4 days ago. So we would put the line in there and evict that one. And then if something were being put in here again that wanted to go in set 0 or was mapped to set 0, then it would evict Thursday next, and so on. Of course, these timestamps will be in the microseconds or nanoseconds, not days of the week. The next thing we need to do here is let's look at a different set associative cache, a two-way set associative cache. Actually, let's stick with the 4 and answer a question. Are there more lines or more sets? There's more lines. There's 4 times as many lines as sets. So instead of mapping to tag line word, it's not possible here. I don't know which line it's going to end up in. So now I'm going to ask questions such as how many bits make up the tag set word? Because within the set, an algorithm determines which line. So you cannot say which line in a 4-way set associative cache. So it's the same memory. I didn't change that. All I did is change this from direct map to 4-way. I didn't touch the memory, so it's still 16 bits. There's still 32 words in a line, so it still requires 5 bits. That hasn't changed. What has changed is there were 8 lines, but there's only 2 sets. You only need 1 bit. It went down by a factor of 4. This was 2 to the 3 lines. This is 2 to the 1 lines. And then the tag goes up for a couple of reasons. First of all, it is showing us it is 16 bits. 10 plus 1 plus 5 is the same as 8 plus 3 plus 5. So when you change from a direct map cache to a set associative cache, don't change the word field at all. This is going to go down by this logarithm, and this is going to go up. The reason the tag goes up is because there's more competition. Main memory blocks are now fighting for 2 things here instead of 8. This is a measure of the competition. If there are 1,000 students fighting for 500 parking spots, there's more competition if there's 1,000 students fighting for 100 parking spots. So that it would require a higher tag. The tag is an indication of how much competition there is. A whole bunch of things get mapped here, and a whole bunch of things get mapped there. So the tag is going to be bigger. So there's a very similar question we could have asked. How many bits make up the tag set and word for the following 4-way set associative cache? And the answer is 10, 1, and 5. Then you could also ask, what's the tag set and word for main memory cell A305? It was word 5, 00101. It's still 00101. It's still the final 5 bits. But the set is the next bit. It's in set 0. So word 00101, set 0, and the tag is the final upper 10 bits. So let's see, that's 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. All right, so let's see, that's 640, 724, or no, 640, sorry, that's not 84. 640 plus 12, 652 is my guess. So that's a good question we could have asked. That's the first introduction to set associative cache. I'm going to stop the video and make another one for a 2-way set associative cache that starts like this.